Now let's look at the problem. Check if a number and its double exists. So the problem statement says that you will be given an array of integers. Check if there exist two indices I and j such that I is not equal to j, and we will be I and j is greater than or equal to 0 and less than the length of the array, and we have to find an index at which basically we will find a number and its respective double. So array of I is equal to twice the value of the value at jth index. So we need to find if a particular number and its double are present inside the given array of values. If so, we need to return true, otherwise we need to return false. So these are simple conditions. So ultimately two values should be at two different indexes, and it should be in the range of 0 to last index, which is nothing but 0 to n minus 1, assuming that there are n number of values in the given array, and the value at ith index should be the value twice that of value at jth index. So ultimately we have to find one such combination. If so, we need to return true, otherwise we need to return false. So here let's look at this example, right? The values we have are 20, 2, 10 and 3. So if we pick 10, twice the value of that is 20. So 10 and 20 are there, so we can return true. And here if we see another example, 3, 1, 7 and 11, right? So there is not even a single pair of numbers where we have matched all these conditions. That is the reason why we will simply return false. Simply here also, see here, this is a very important example. 0, 1, 7 and 11 we have. Now here we have 0. Twice the value of 0 is nothing but 0 itself. But 0 is present only once. If at all we had 0 at some other index, then we would have returned true. But here 0 is there only once, and we need to have twice the value at another index also. That is the reason why here we are returning false, and we don't have any other pair as well where we satisfy all these conditions. Okay, here if you take this example, we have 0, 1, 7, 0. Twice the value of 0 is 0, and it is present at some other index where I is not equal to j, so we have returned true. Okay, so this is very important examples that we have seen in the end. Last two examples are very important in the case of handling the conditions for the value of 0. Now that we have seen the problem statement and what are the various cases that we can see, let's try to solve the problem using the brute force approach, right? So in the case of brute force approach, basically what we can do is either in the effective implementation that we will be writing later on, or even in the brute force approach, if there are not even two elements on the given array, right, there is no need of writing the business logic, because array itself doesn't have a two values minimum. Then how can we have a value and its double, right? So we can have all these validations in place, but here I am writing the main core logic. So here, as part of the brute force approach, what we can do is we can write the loop from one loop with the variable I from I0 to very last index, and similarly we will have another loop j starting from 0 till n minus 1 as well. Immediately what we will do is, if at all I is not equal to j and the value at ith index is equal to twice the size of the value at jth index, then we have found one such pair, so we can simply return true. Okay, if we check all the scenarios, as long as these loops are running, in each and every step we will increment it by 1. Here I will get incremented by 1, and once we check all the scenarios, if there is not a pair like that outside the for loop, what we will do, we will return false. Okay, so this is the brute force approach for finding a pair where a particular value and its double are existing. And here we need to return true and false based on the availability. If at all, if your problem statement mentions that you need to return the indexes, you can return a array or list where we can have this I and j and return that. But here we are simply returning true or false. For this, the time complexity will be, in the worst case, this outside for loop can run for n number of times, and here the inner for loop can run for n number of times. As a result, if we basically not n number of times, so here we are running till n minus 1, right? So the last particular value and its double can be last two values. So here we will be running till n minus 1 and here we need to run till last value. So if we simplify the time complexity of that, the time complexity will be order of n square, but the space complexity will be order of 1 itself. So here order of n square time complexity is very huge. If at all the array size is in millions or something like that, right? Basically an array which has huge number of values. So our aim is to bring down this time complexity and write the effective solution. That is where binary searching is going to come into the picture. Obviously we can't apply binary searching on a non-sorted array, right? And the problem statement did not mention that the array is sorted as well. So our first step in the application of binary search basically involves sorting of the array and then trying to find the value and its respective double are present in it or not. If so, we will return true or false. Now that anyway we understood the brute force approach, now let's quickly understand how can we solve this problem using the binary searching technique. So here the array is not at all sorted, right? So the problem statement did not mention that we have gotten a sorted array. So first step of applying binary searching technique is sorting this array. So first, as part of the first step, we will sort the array and the sorted array will be 0, 2, 3, 4, 5, 7, 10 and 12. So we have gotten all the values 3, 6, 8, 3, 6, 8. So this array is sorted. Now what we can do, we can start iterating and we can pick up a value and we can check if its respective double is present using the binary search on the same array. So whatever the inner loop that was running for n number of times, we can bring that down to log n iterations. That is the reason why whole time complexity of order of log n square comes down to order of log n. So here we have already solved the binary searching algorithm, right? So the exact utility function we will be using inside the iteration logic. So how that would look like is, let's just say we are starting from 0. 0's double is 0 itself. So here there is no 0 at some other index, so we will not return true or anything. We will simply move on to 2. Once we pick up 2, we are looking for twice the value, which is nothing but 4. So we will check in the array if we have 4 or not. Since we have 4 and it is at a different index than where 2 is at, the condition is matched, so we will immediately return true. Simple implementation. First there are 3 steps ultimately. Okay, sort the array and then start the iteration, and in that iteration pick up value, and once we pick up the value, apply binary search and check if that double is present. So how we will do that? Let's quickly write the pseudocode for that. Okay, so here we will write one function find a number and double are present. So what it does, it will take the array of values. As part of the first step, what we will do, whatever the validations that you can have, if the array has less than 2 number of values, those things you can put, but here I'm trying to write the main business logic. So as part of the first step, either merge sort or quick sort, whatever we use, we can sort the array. Okay, so we have sorted the array. Now what we will do, we will start a loop I from 0 till the length of the array, which is nothing but n, and in each and every step we will increment it by 1. Inside this loop, what we will do is we will apply the binary searching technique. So let's just assume that we have one function called binary searching function, and this, let's just assume that it will return a index, and we have a binary search function. What it does, it will take the array and it will take the target it need to look for, and it has all the business logic, and it will return -1 if the value is not available. Otherwise, if the value is available, it will return a valid index. Okay, so that is what here. Now immediately what we will do is we will call this binary search function with the sorted array, and the value we are looking for is twice the value that we have at ith index. So a of I into 2 we will be passing. Now this function will return an index, right? We will store it in one variable. Immediately what we will do is, if the index is not equal to -1, if the value is not available, it will return -1. Along with that, whatever the index that we have gotten is not equal to I. Remember that this check is very important for the value of 0, because twice the value of 0 is 0 itself. That is the reason why if you don't write this condition, there is a chance that for the value of 0, I and index can have same index and it can appear only once. That is the reason why this check is very important. If this condition is not matching, then we have found I and its respective double at this index. So what we can do, we can immediately return true here. Otherwise, we will simply move on to the next element, and further I gets incremented and its respective index and respective twice value will be searched again, and all those things will keep on going. Once this loop is completed and we still not have returned true, that means that there is not even a single pair where a number and its respective double are present. That is the reason why outside this for loop, what we can do, we can return false. Okay, so this is the pseudocode for the solution using the binary searching technique. So if we want to calculate the time complexity, let's just assume that we are solving it using merge sorting or quick sorting. The time complexity of it will be order of log n, and here the outside loop is running for n number of times, and inside we are applying the binary searching technique, so it will have log n. So ultimately for this looping, the time complexity will be n into log n. So the total time complexity will be order of log n plus order of n log n plus order of n log n. It will be twice that of order of n log n. Sorry if I had said the sorting will take order of log n, that is not the case. It will take order of n log n. Merge or quick sorting, which are best for sorting, will take order of n log n time. Okay, and the space complexity will be order of n itself, because for the sorting we will take order of n units, but for the remaining portion we are taking constant only, but for sorting we are taking order of n units of memory. Okay, so that is the solution. Here, even though we brought down the time complexity from order of n squared to order of n log n, the space complexity is order of n. If at all, if we are using additional space, why can't we bring down this even further? So that is where using hash maps comes into the picture. If at all, if you want the solution of this problem using the hash map, you can use the problem link in the description, which will take you to codingpal.org. There I have documented as well as checked all the scenarios for checking if a number and its double are present in the given array of values or not. Okay, so that's it for this one. I'll see you in the implementation part.